A few moments later.
Guys, I made this Milo 20 minutes ago, but it's still hot. Why so slow? Oh no, maybe your Milo is cursed. Maybe it refused to cool down. Huh? Sabrina, please lah. Okay, listen. Your Milo isn't cursed. It's just science. When the Milo is very hot, it cools fast. When it gets closer to room temperature, it cools slow. That's Newton's law of cooling.
So that's why the Milo is not angry? Just doing science?
Oh wow, even Milo follows rules better than me.
That's what we are talking about today's Newton law of cooling. Also, how the temperature change over the time.
Let's begin our presentation!
Based on the video shown earlier, we can observe that a hot drink like Milo cools down faster when the surrounding temperature is lower. This phenomenon can be explained using Newton's law of cooling. Now, I will start with an introduction to this topic. Newton's law of cooling states that the rate of an object temperature of a body is proportional to the differences between its body temperature and the surrounding temperature. According to this law, a hot object cools at a faster rate when the temperature differences between the object and its surrounding is large, and the rate of cooling decreases as this difference becomes smaller. Now, I will be explaining about the formula. T is the temperature of the object at time. Tm is the temperature of surrounding object. dt over dt is a rate of change of a temperature. T minus Tm is a difference between object and its surrounding temperature. Also, K is a constant of proportionality. For example, a warm laptop will cool down faster in aircon room rather than in a room without aircon. For the second one is, a bottle of a warm water will cool down faster when it was placed in a refrigerator rather than when left on a table at a room temperature.
Next is problem statement. A cup of hot Milo is freshly prepared at an initial temperature of 92 Celsius. The surrounding room temperature is 27 Celsius. After being left on the table for 4 minutes, the temperature of the Milo drops to 70 Celsius. According to Newton's law of cooling, the rate at which the Milo cools is proportional to the difference between its temperature and the surrounding air. However, the exact cooling constant and the time required for the Milo to reach a comfortable drinking temperature of 50 Celsius are unknown. We have two questions here. First, determine the cooling constant and the equation represent the temperature of the Milo at any time. Second, calculate how long it will take for the Milo to cool from 92 Celsius to 50 Celsius.
I'll be explaining on the solution to the problem. First of all, I make table that summarize the information given in the problem. At time 0, right when the Milo is freshly made, its temperature is 92 Celsius. This is our initial temperature. After 4 minutes, the Milo has cooled down to 70 Celsius. We will use this value to calculate the cooling constant K. And on the last row is what we want to find, which is how long it takes for Milo to reach 50 Celsius. So on this side, we also have the room temperature, which is 37 Celsius. This is the room temperature, where denoted by Tm. The Milo will cool towards this temperature. So to answer the first question, the first step is use the formula of Newton's law of cooling. Here, T is the Milo's temperature at time T, Tm is the room temperature, and K is the cooling constant that we want to find. Next, we separate the variables and integrate both sides. Then, simplify the equation using exponential to get the general solution. Here, A is a constant. Then, we substitute the room temperature to complete the general solution. Now, to find A, we substitute the initial temperature 92 Celsius at 0 minute, and we found that the value of A is 65. Next, we substitute the temperature at 4 minutes, which is 70%, to find K. The value of K is 0.1033. Finally, we substitute the values of A and K into the equation, into the general equation. So now, we get that the answer for the temperature of the Milo at any time. Onto the question 2, where we need to calculate how long it takes for Milo to cool down from 92 Celsius to 50 Celsius. Here, I attach the similar table for reference. By using the equation of temperature Milo at any time t, we substitute 50 Celsius into the equation. Then we solve it, and we will find that at 50 Celsius, the time is 10.1
From this
minutes.
investigation, we can see that Newton's law of cooling accurately describes how the temperature of the Milo decreases over time. By using the initial measured temperature, we were able to calculate the cooling constant and form the temperature equation for the Milo at any time. With this model, we also determine how long it takes for the Milo to cool from 92 degrees to a comfortable drinking temperature of 50 degrees. Overall, this shows that Newton's law of cooling is useful for predicting real-life temperature changes and help us estimate when a hot drink becomes safe to enjoy.